Now that we understand what is the concept of pressure line, in type 1 members, the pressure line has to be always, the EC has to be always less than, EC always has to be less than KT and KB. Okay. So, this is what we said. What is EC? EC is the location of your compression force from CGC. Now, let us look at the cracking moment is defined as a moment. We have studied that previously also. The cracking moment is the moment due to external loads at which the first crack occurs in a prestressed flexural member, right? And that is function of your FCR, and FCR we take that as 0.7 square root of FCK, right? And FCR is defined in terms of FCK, and we have seen it is 0.7 square root of FCK, right? Now, for example, for a simply supported beam, FCR will be reached at the bottom fiber, right? And then you can calculate what is the moment that it can withstand, so that at that point of incipient of cracking. Now, how do we do that? Again, that we have seen. If you see here, now here we are writing here as PE. Okay. Now, the PE we have studied that there is initial prestress, there is P0, and then there is PE. Okay. And PI is the initial stretching that I give, P0 is the stress after transfer, and P is the effective pre-stressing force, effective pre-stress at service, right, at service. So, you see here this is considering after considering the losses, right. So, if you have PE that is acting, now what is the distance at which the P is going to act is nothing but your eccentricity of your cable, and this section is also subjected to cracking moment. That is what we are trying to calculate, so that the net effect will produce stress at bottom of FCR, which is tension. So, this is plus and this is minus, and FCR value from code we know it is 0.7 square root of FCK. Now, how do we calculate the stresses? We know that there is a concentric component, negative PE by A is always compression, which is negative, and then I am calculating stress at the bottom and pre-stress force moment PE into distance that we are calculating, P into E, I should say this is P into E, right, YB by I, that is going to create this, and then you are going to have FCR, that is equal to your PE into E. Okay, this is also should come also into E. Okay, so not here, E into E by Y. Okay, so the E should be here. Similarly, you can see that P here it is there, right. So, I can say okay, E is missed out here, but this is effective pre-stress multiplied by E will give me the pre-stressing moment, and I am calculating the stress at the bottommost fiber. So, IB by I. So, when you simplify that, I get the expression for my cracking moment like this. So, we have already seen that the moment you know the section properties, I know IB, I, A and so on, and if I know the effective pre-stressing force and the location of my pre-stressing force, I know this value, I can calculate my cracking moment, okay, which we have done that. Now, how to get this cracking moment? Just using kern points. So, that is what we are trying to see. So, now you see here this is the location of your resultant moment. For type 1 members, we have always seen that when C is within the less than KT and KB, always the stress at the bottom fiber will be 0, or I should say that the stresses will never go into tension. That means, when C is at the location of your KT somewhere here, I will find that this is the stress, this is going to be 0. When C is at KT, right. Now, what is this? This is an additional stress that is being created. Now, what is the additional stress that is being created? When the C moves away from KT by some distance, which is delta Z, then what is the moment that it is causing this additional stress? That will be C into delta Z, right. So, this plus this will create a tension stress of positive FCR at the bottom. Now, we try to find out what is this delta Z, or in other words, if FCR is given, we can find out what is the maximum distance delta Z the C can move away from KT. Okay, now let us look at it. How to get your M cracking that it is creating this stress is basically you will find that now C is acting at a distance, you can see that initially C will be at location of your this location, C will be there. Now C has moved up. How much it has moved up? This much distance. What is this distance? It is going to be E plus EC, right. So, when C is acting at this location EC, the moment it is, that is what it is creating this stress profile of FCR. So, the moment that is produced is going to be C into E plus EC. Now, EC is nothing but KT plus delta Z, right. So, we can see what is EC here. So, this is the thing, right. So, EC is nothing but this plus this, that is nothing but delta Z plus KT. And now, what is delta Z? Delta Z is created by this moment. If you just see that this is nothing but it is creating this additional stress. This is also additional stress of FCR. So, now what is that it is being created by this additional stress, which is nothing but additional moment it is created by this delta Z. C into delta Z your MCR, right. So, it is basically FCR into I by YB, because this stress FCR is created by a moment which is this, which is FCR into I by YB, right. So, now the expression for my cracking moment is going to be C into E plus KT plus FCR into I by YB. Now, you see that C is equal to PE, which is the effective pre-stressing force, KT is R square YB and R square is nothing but I by A. Then if I substitute all these things, then you will find that whatever we did previously, that same expression for cracking moment can be found out. So, in a way I can just use KT and effective pre-stressing force and FCR and sectional properties and get my MCR, which is exactly same as that what we did using stress method of analysis. They are all one and the same, but this is just a simple expression. This expression, if you see, this is a simple expression in terms of just KT and KB, maybe we can say, okay, KT and FCR and sectional properties like I and E, so on, right. So, finally, they are all one and the same. So, this is just a simple expression only in terms of your current points. Using current points and other sectional properties also quickly you can find out your cracking moment. So, because now when C has moved away by this distance, it is what it is creating the stress. So, we are just decoupling EC as KT plus delta Z, and delta Z, the C into delta Z is created by this stress. So, that is what we are replacing this, right. That moment is nothing but this. This is the moment that is C into delta Z, right. So, when we add that, you get the same expression. Now, let us see what are the crack widths. Now, we are not getting into the detailed calculations of crack widths, but we find that again in type 1 no tension. So, in type 1 under service no cracks, right. In type 2 again crack widths, it can go into tension, but typically the tension values will be less than FCR. So, again type 2 also no crack. In type 3 you will have tension can exceed FCR, but you will have limits on the crack widths typically. Okay. So, typically crack width is calculated to satisfy the limit state of serviceability. Among pre-stressed concrete members, there is cracking under service loads only for type 3 members. Okay. So, in type 1 and type 2 also no cracks, but in type 2 tension is allowed, but no crack. But in type 3 tension is allowed and also it can crack, but the crack width has to be limited, right. So, the crack width is calculated for cracks due to bending which occur at the bottom or top surface of the flexural member. Now, class 20.32 of IS 1343 specifies limits of crack width and so that the appearance and durability of the structural element are not affected. Okay. So, typically in a pre-stress member, it is always better to go for a under service load, it should not crack. Then you will have, you can use the entire amount of inertia in your deflection calculations, and also the durability performance will be much better. Now, what are the limits? For crack width has to be less than 0.1 millimeter for members that are exposed to aggressive environment like this marine environment or which are rich in chlorides, and crack width has to be less than 0.2 millimeter for all other members. So, crack width cannot go more than 0.2 millimeter in pre-stress system. Now, what is camber? Again, camber is also a very important aspect in design of pre-stress members. Let us say most of the time what will happen, your tendons will have some eccentricity, because we want to maximize the benefit of pre-stress, as we have discussed in the very first class. If I always put pre-stressing at an eccentricity, it is going to help me in better performance. So, typically the eccentricities are toward the soffit of the beams to counteract the sagging bending moments due to transverse loads, right. Now, what will happen, because I am applying pre-stressing like this, always the member will tend to camber upward or deflect upward, okay, that we call that as a camber on the application or transfer of pre-stress. The moment the pre-stress is transferred, then the member will camber up. Now, this is the example. For example, you see an I-beam, you see the amount of camber, it is lifted up like this, right. And that means my pre-stressing cables are running somewhat like this, right. This is your CGA, okay, this is your CGC, and this is your eccentricity. That means I have created a moment that is basically pushing the beam up, right, due to pre-stress. So, this is a camber. And this is for a T-beam. Again, you see any pre-stress system, you see, you have all the pre-stressing that is there. But if you look at the overall pre-stressing, CG will be somewhere here, and that is creating an eccentricity E with respect to CG, and that is basically creating an uplift or a deflection upward, which is called as a camber. Camber is actually good, but if you apply too much pre-stress also, then you will have problem, as we discussed, then you will have cracks on the top side. Okay. Deflections. Now, let us go to the deflections. The structural concrete members always should be designed to have adequate stiffness to limit the deflections, otherwise it may affect the strength or serviceability of the structure at working loads. Right. Now, let us see what are the factors that influence deflections. Of course, how much load that you are putting, the self weight of the member, and if you have a very stiff concrete, always the flexural rigidity EI has to be high, and E is function of your FCK, we know that, right. And modulus of elasticity also helps. That is the reason for high strength concrete, typically E will be higher. They tend to, if you have same cross section, then they tend to reduce the deflections. And second, moment of inertia of moment of area of cross section or I, that makes a difference. And span always, that is again when you want to go for a longer span, that is why you go for pre-stressing, because the deflections will be less. And the magnitude of pre-stressing force also, and fixity conditions, boundary conditions. And another important aspect is the shrinkage, creep and relaxation of steel also will increase. So, these things will produce something called as long-term deflections. Long-term deflections. Okay. Now, let us see what are those things. So, we have short-term or instantaneous deflections. Deflections can be categorized into two things, long-term deflections. And short-term deflections are usually governed by the bending moment distribution along the span and flexural rigidity of the members. And typically, gross moment of inertia is used in the calculations. And this stage is called as pre-cracking stage. Okay, typically it is called pre-cracking stage. The moment you have cracking, creep, shrinkage, all these things comes, the long-term deflections are governed by the sustained load. Now, what is the sustained load? Typically, we take full fraction of a dead load plus some 25% for live load. Okay. So, that is a usual thing. Okay. These are called sustained. You take always 100% of the dead load, because that is always going to be there, and some fraction of your live load. Some course may take 25%, some course may take 40%, that is up to them. So, this is typically a sustained load. So, while computing the long-term deflections, again effective modulus will be there. I think again we see that EC will reduce, right, due to creep. Similarly, ES or EP again will reduce due to relaxation, right. So both of them will soften the material. When the elastic modulus is reducing, deflections will go up, right. This typically happens in post cracking stage. Okay, now how do we get your deflections? As I think most of you would have studied strength of materials or in your structural analysis, Mohr's theorem. And Mohr's theorem, what does it say? If I know the elastic curve, for example, you see a simply supported beam which is subjected to some let us say generic load, right, W, which is varying. If I want to measure the deflections between point B and C, for example, let us say here, and let us say you have this deflection like this, right. So, this is point A and this is point B, right. So, let us say this, I have support like this, it is deflection. So, this is your elastic curve. So, what is that we do? The vertical deviation of point A on the elastic curve with respect to the tangent which is extended from another point B equals to the moment of area under M by EI diagram between those 2 points A and B, right. So, the vertical deflection of, let us say this is a point A and this is, let us say, at point B, or maximum point, let us say we have point P. Then you draw a tangent and how much it is deflected, let us say you draw a tangent like this and then you extend it. This deflection is basically given by the moment of the area under the M by EI diagram. Now, what is M by EI? M by EI is nothing but your curvature that we discussed. That is your curvature for elastic systems, right, between the AB. So, this moment is computed about point A where the deviation from point B to A is to be determined. So, we take take this moment about point A to calculate, for example, this is the shaded area of M by EI, this is an M by EI. Okay. So, we take this moment. So, the Mohr's moment area theorem are typically readily applicable for estimation of deflection. So, now we can use the same moment area theorem that is given by Mohr for calculating the deflections for prestressed beams. Now, EI is your flexural rigidity of the beam and X is the distance of the centroid of the BMD. For example, this is your X. Okay, we are calculating where the centroid of the center, and you see here this is nothing but your M by EI, right. That is your curvature diagram, it is nothing but your curvature distribution. Okay, now how to get this? There are two theorems. The slope between the 2 points is nothing but the area of the bending moment divided by the flexural rigidity, that is your theta, that is your first. We just calculate the area of your M by EI diagram, that will give you the slope change between the 2 point segments, between A and B, let us say you are doing it. So, that gives me the slope change between the point A and B. Now, the vertical deviation of one point with respect to another is given by moment area of BMD divided by flexural rigidity. That means, I am taking the M by A diagram and I am integrating it and I am taking that moment of that area, right. So, that is nothing but your AX by EI. A by EI is slope into distance X will give me the deflection, right. Now, the below example shows, for example, for a beam with a straight tendon with uniform eccentricity like what you see here. For example, you see here I have a beam that is having pre-stress to a force of P and it is having constant eccentricity of E. Now, what will be the BMD that is created by this pre-stressing force? It is nothing but P into E, right. So, that P into E is a bending moment that I have created along the length of the member. Now, if I want to calculate this area, right, then again I have to divide this by EI and get by area. So, how do we do that, right? So, the area is nothing but, let us say I want to calculate the deflection at the midpoint which is here. So, now let us say from here to here. So, basically I load this divided by EI, okay, BMD divided by A, that should be the loading, and then I calculate from here to here. So, what is the area? Area is nothing but PE by EI, this distance is now L by 2, So, PE by 2 into L by 2, and then I take moment of this about the point A. So, the CG is going to be at a distance of L by 4. Okay. So, this is your area, this is your area times your x divided by EI. So, if you substitute that, you are get vertical deflection, which is A, is nothing but PE times L square by 8EI. So, this value, the deflection, which is A or delta, is nothing but PE into L square by 8EI. Okay. As per this, it is A, area is nothing but your moment area of your bending moment diagram, and then you divide by EI. EI also should come, right, because we always load the beam with curvature diagram and then we try to get it. Moment divided by EI is nothing but your curvature. Okay, now let us do one quick example that will help us to understand these concepts. For example, we take the same cross section, 500 flange width, 200 mm thick and a 1 meter deep beam, which is having a breadth of web equal to 150 mm, and it is having some pre-stressing steel. The details are given here, and that is at a distance of 100 mm from the bottom of the flange. And even here you can see that eccentricity here is 400 millimeter at the center, and eccentricity here is 0, and here we see this is what we are saying, that eccentricity is 400 millimeter, and length of the beam is 20 meters. Moment is given to you as 800 kilonewton meter, and pre-stress transfer is 2500, and 15% loss is assumed to be happening. That means PE, effective pre-stressing force, is nothing but 0.85 times P0. So, that is what we are saying, right. Now, grade of concrete is M40. These are the details that are given to you. Now, we want to analyze this beam. Okay, let us see. What are the things that we want to analyze? We have to first calculate Kern levels. This is purely from sectional property. That means it has nothing to do with what kind of pre-stressing I put. Once the geometry of the section is given, you can calculate your Kern level. Cracking moment, then we need to know what is the FCR and then what the allowable load that it is acting. Location of a pressure line, so that means we are calculating EC location, that is a pressure line. Now, stresses at the top and bottom fibers at transfer and service. Now, deflection at midspan due to its self height and pre-stress. Now, I am given some stress limits that need to be satisfied for both the tension and compression, for transfer as well as service. Okay. In pre-stressing, always we have seen there are 3 stages: transfer, service and then ultimate. Okay. So, in RC typically we will have only 2 stages, typically service and ultimate, but in pre-stress we should also do the analysis at transfer. That means when you transfer the pre-stress, what kind of loads that you are acting, all those things that we have to consider, and these are the stresses in compression and tension. Now, let us see how to do the analysis. As we see, the first thing is, let us calculate the geometry of the cross section. That this is the same cross section that we have been using in this course. So, it is the same, and if I divide this into rectangles, you can see A1 and A3 will be equal to 100,000 millimeter square, A2 will be equal to 600 into 150, that is 90,000 millimeter square. So, total area is 290,000 millimeter square. And this is a symmetrical cross section. So, centroid is going to be 500 mm and YB is also going to be 100 mm. So, YT is also going to be, so everything is going to be symmetrical because it's a symmetrical cross section. Now, the eccentricity of the pre-stressing steel is Y is minus 100. So, it's going to be 500 minus 100, which is 400 millimeter, which is given to you. Okay. Now, the moment of inertia, again we have discussed this. If I divide this into number of rectangles, I1 and I2 are basically nothing but your rectangles at top and bottom. So, this is BDQ by 12 plus A into distance of this centroids. of the element with respect to the overall centroid. So, that works out to be 1.633, you know how to do it, and I2 is basically, because here as per parallel axis theorem, the centroidal axis and the of the whole system and the middle rectangle is one and the same. So, this will become 0 that. So, this is just 1 by BDQ by 12. So, you get this value. So, the overall moment of inertia we know, which is I1 plus I2 plus I3, which is 3.53 to 10 to the power of 10, and radius of gyration is I by A. So, you get this value. Now, kerns, as I told you, kerns of the section, the first question that what we have been given is R square by YB, which is this, R square by YT, which is this 243, 240. Because it is a symmetrical cross section, we see that it is KT is equal to KV. This is 243.45 and 243.45, right. So, we got this. Now, I want to calculate cracking moment. So, cracking moment, when you do the prestressing, we need to calculate what is the effect of your moment, right, service moment due to, self-weight moment. Now, how do you get your self-weight moment? We know the unit weight of concrete multiplied by area, we know the per meter length, it is going to be 6.96 kilonewton per meter. For simply supported case, the moment due to dead load is WDL L square by 8, then you get 348 kilonewton meter. So, load into span square by 8 will give me 348 kilonewton meter. Now, what is cracking moment? Modulus of rupture we know 0.7 square root of FCK, 4.43 megapascal, and then you get stresses at the bottom. I mean, you can calculate from MCR, we already derived this equation, right. So, we just derived previously, so we just plug in and you get value. Now, you see here what is the effective prestressing force is, if you see that it is going to be 0.85 into 2500. So, we are assuming 15% loss, that is the reason this 0.85 is coming. 0.85 into P naught times moment of inertia divided by area into YB. This is your second component. The third component is again PE, which is effective prestressing force, which is 0.85 into 2500 into 400 is your eccentricity. So, if you do that, your cracking moment works out to be 1680 kilonewton meter. And you see that the live load moment corresponding to cracking will be, I can apply now additional moment of, this is self-weight moment. So, that means this is the moment at which it is going to crack. So, I have to apply 1680 minus 348 to crack. Now that we have got only applying 800 kilonewton, this is given to you in problem statement, MLL is given to you, right. So, hence the section will behave as an uncracked section, because this 1332 is much higher than 800. So, the section is not going to be cracked for the given distribution of the load, right. So, I can use gross moment of inertia. Let us say if this MLL is greater than this 1332, then I will not be IG, it will become I effective depending upon the moment that it is acting, my effective moment of inertia that I need to use. But in this case, because my live load moment is less than the reserve moment that I have to crack, so it is going to be uncracked. Okay, now we have done two things, kern points and cracking moment. Now, let us look at how to calculate the pressure line at the midspan location, right. We are looking at midspan location. Now, at transfer, again two things, at transfer only dead load moment is acting, dead load moment and maybe moment due to prestress is acting, right. So, at transfer, that means the C is going to move away from T. How much it will move away is proportional to the amount of dead load that it is seeing in that particular cross section. Dead load moment we have already calculated. At transfer, again what is the force? C will be equal to P naught, okay, there is no losses, transfer. So, it is this. So, you see that the lever arm is 139.2 millimeter, and if you calculate your EC is nothing but lever arm minus the eccentricity, and if you see eccentricity is 400, you get a negative value of EC. That means what? EC is below the CGC of the cross section. ECG eccentricity of compression force is still below the CG of the concrete area. So, it is still not moved up. So, it is still below the neutral axis, we can say. So, EC is negative. So, the pressure line is going to be below CGC. Now, you see here the EC is greater than KB. KB, what is that we got? KT and KB equal to 243.45. Now, what is EC? Now, I got 260.8, which is greater than 243. There is going to be some tension at the top. So, that means we are violating and for this particular amount of pre-stress and this condition, I am going to have some tension that is developed at top. And so, it is not strictly a type 1 member.